Good morning.
Good morning. Who's talking? Javier?
Yeah, that was me.
Okay. Saki, I'm sorry, Javier, I don't mean to be rude to you. I just have a thing. Saki, are you okay? Saki. She's connecting. How's it going, Javier?
I'm doing good. What about you?
Peachy, what is that thing behind you? Ah, okay. I saw these two things hanging down and what it looked like were hedge clippers. And I was wondering why in the world you would have hedge clippers attached to the wall. Okay. Saki's here. Let's see who else is here. Yes, she's here. Max, you here? Yep, you're here. Charlotte? Charlotte?
Hi, how are you? I'm sorry I missed last week. It was
No problem. It's what's important is that you're here this week because this is the week that keeps you in class. Okay.
That's my goal. Thank you.
Go through, read through the syllabus, see if you understand everything, and if you don't, we'll go through it. Okay.
I watched last week's video too, so I got up to date with all that.
All right, fantastic. You know, that is the one thing that's a godsend about these Zoom meetings. Sorry, the fact that I do videotape them, and so you get a chance to get on with them. I got to finish roll here. Sorry, Charlotte. Is it Charlotte? How do you?
It's Charlie.
Charlie.
Mm-hmm.
Thank you. Doodley. Just speak of the devil. Carson. I'm not. Yes, I see you, Carson. Samir. See you, Samir. James. God, I'm just saying the names and they're popping up. Arthur. Arthur here. Is Arthur here? Aditya was here. Francisco.
Yes.
Thank you. Tin, I saw you come in. And Javier. Okay. Is there anybody whose name I did not call?
Did you call my name, Professor?
I did. Yeah, I did not call your name because you were like one of the first people up there and I had already crossed you off. Would you like me to call your name, Aditya? Aditya. Okay. You didn't say here. All right, I'm going to take off the fact that you didn't say here, so obviously you're not here.
Professor, you already counted my name.
I'm sorry, Javier, do you have a question?
It's Aditya.
I'm sorry, it's who?
Aditya.
Aditya. I'm sorry, what did you have to say, Aditya?
Oh, did you call my name?
No, I didn't. I didn't call your name because you were one of the first people in here, okay?
Okay, thank you.
So you are in here, you are recorded. As long as you say here. Did you say here, Aditya?
No, that's the reason I asked you because you already counted my name, so I just want to make sure.
Yeah, but you haven't said here yet, so how do I know you're here? Unless you say you're here.
Okay.
Oh, I'm here.
All right, fair enough, guys, fair enough. Are we doing okay?
Sorry.
I didn't hear my name either. Professor Faye Aiken is here.
Faye, I got you already.
Thank you.
To Faye, you're indelible upon my mind. You just bother me so much this early in the semester that I've got you in there and I want to get rid of you as soon as possible. Okay, Faye?
Sorry, I have a lot of questions.
Please keep on asking. Faye,
I'm sorry, did you call my name?
Who are you?
Doodley Bellevue.
Doodley, I got you. I got you. I called your name right as you popped up on my screen.
Oh, okay. All right.
All right. Everybody in here? Everybody don't want. I got some people that are here because they want to be, and lots of you that are here because you don't. Faye, you haven't changed your smile.
I'm sorry?
You haven't changed your. You got the same expression on your face this whole time. You got your picture up rather than live video, Faye.
Yeah, it's cuter than my live self, so.
It's 9:30 in the morning. I understand. Hey, this is what my hair looks like at 9:30 in the morning. That's why I wear a hat. We doing okay, guys?
Yes.
All right. Do you remember back last semester in intro, the first lab you did was chem and physical changes and properties. Do you remember back that far?
Yeah.
Hell,
Mhm.
I mean, some of you probably can't remember what you had for lunch yesterday, but you remember what it was? It's a subject that's kind of hard to wrap your mind around. So I'm going to do my best to try and drag you kicking and screaming so that you have an understanding of this, okay? Okay? That's the plan?
Yes.
Do I have your permission, Saki, to go ahead?
Yes.
Guys, she's saying no. So let's,
I didn't say no.
okay, guys. What I'm going to do, I prepared a PowerPoint for this class last semester. I'm going to use that, but I'm going to hold off on it for a second or two. What I'm going to start with is what I prepared for my 1025 class, which gets things on a better footing. Are you seeing the slideshow?
No.
Okay. Let's go back here. Share screen. Now are you seeing it?
Yes.
Thank you. You see the way it works? I ask a question and I have to sit here and be quiet for a while until somebody answers. So who said yes?
Faye.
Hey, you are now my designated yes person. Whenever I
Oh.
need a yes, I'm going to ask for Faye, okay?
Okay.
Chem and physical changes and properties. We're dealing with 4 different issues here. We're dealing with physical properties, chemical properties, and we're dealing with physical changes and chemical changes. So we're going to deal with these kind of one at a time. And basically, if we're dealing with a physical property, we're looking at what makes a substance that substance. Okay. Let's see. Max.
Yes,
Max,
sir.
what makes you you? You like to fidget around a lot, I've noticed.
My genetic makeup.
Okay, your genetic makeup. All right. That means that you have kind of brownish red hair.
Yes, sir.
Brownish red hair. Okay, that's what makes Max Max. Okay, he's got a trait. Similarly, all substances have traits about them that make them what they are. Those traits or characteristics are the property of the particular substance. Now, what's great about this, since every time we have that particular substance, it exhibits the same properties, we can use that property to identify it. So that's a great thing about physical properties. We use physical properties to identify them. Water boils at 100 degrees. Water has a density of 1.00 grams per milliliter. So basically, if I've got those 2 properties, I can feel fairly certain that if I'm looking at a clear liquid, it's water. Physical property, what makes it what it is. Now, if I'm dealing with physical changes, what I'm doing with the physical changes, I'm changing how that substance is observed without changing the substance. Okay, I have a piece of paper. What can I do to this piece of paper that will change it?
Fold it, tear it.
Terrible.
Fold it. Now I folded this. Will it burn like the unfolded piece of paper will?
Yes.
Does it have the same texture? Does it smell the same? I haven't
Yes.
changed it. I could tear it. Is this piece of paper any different from this one? So
No.
they are the same. I have changed it physically, but I haven't altered the substance. I have the same substance that I started with. All right, how many of you have ever boiled water?
Me.
All right, when you boiled that water, have you ever put a lid on top of it?
Yeah.
All right, you take the lid off and you look at the liquid that's in the top of the lid. Is it changed anything from the water in the pot?
No.
Yet what we did was we changed its state. We changed it from a liquid to a gas, then we changed it back into a liquid again. So we changed its state, but we didn't change the substance. I could take that piece of, I have a talent, ladies and gentlemen. If given the directions, I can fold a napkin into a Christmas tree. I demonstrated it at our last Christmas dinner. That's the extent of my origami abilities. Pretty, this looks pretty, right? You can take a piece of paper and fold it. You have physically changed the paper, but it's still paper. This would burn if I put a match to it. But we're not talking about paper. We're talking about specifically chemicals. And when we're dealing with chemicals, the main physical changes we're going to be interested in are changing the state of matter, going from a solid to a liquid to a gas and back, going straight from a solid to a gas, going straight from a gas to a solid, or dissolving it. All of those things, I have changed the form of the substance, but I haven't changed the substance. Let's see, who am I going to bother? Samir. You here, Samir?
Yes, sir.
Samir, have you ever made Kool-Aid in your life?
Yes.
All right, you take cherry Kool-Aid, right?
Right.
Okay. You take cherry Kool-Aid. What does it look like?
It's, wait, you mean the mix or
Yeah,
after
the
it's
mix,
mixed?
the mix.
It's a pinkish powder.
Okay, pinkish powder. All right. What does water look like?
It's a translucent liquid.
Clear, translucent liquid, right?
Right.
I put the Kool-Aid into the water. I've now made the water red.
Right.
Have I changed the Kool-Aid?
Um,
If I take that water, evaporate all that water away, what am I left with?
the Kool-Aid.
I'm left
The
with
Kool-Aid mix. Yeah.
So I haven't changed the Kool-Aid mix, have I?
No.
So dissolving something, no matter that I have changed the color of the water, I have not changed anything. The water is still water. If I evaporate it off and collect it like with the lid, that's still going to be water again. The Kool-Aid, because it's all evaporated down and I have the powder again, I haven't changed it physically. Same thing. If I take something like copper chloride. Copper chloride, if I look at it in the jar, blue crystals. I take those blue crystals, dissolve them in water. My water turns blue. I have not affected a chemical change. I have affected a physical change. Because if I evaporate that water away, I am going to get those blue crystals back. Does this make sense to you?
Yes.
Now, you have to understand English, and you have to understand English semantics. A change implies the action has already occurred. Okay? So, if I give you a statement, I folded the paper. Have I changed something?
No.
Its physical appearance.
Have I changed something
Yeah.
physically?
Oh, yeah.
I went through the act of folding the paper. I folded the paper. On the other hand, if I make a similar statement, the paper can be folded. Have I done
That's-
anything?
No.
No.
Therefore, it is a property. Are you understanding how you got to look at these things very carefully to get the semantics behind what a property is and what a change is? Does that make sense to you?
Yes. Yes.
All right, now we're going to go into chemical. Now, a chemical property is the ability to change into something else. It's not saying it occurred yet. A chemical property is the ability to change into another substance. I have a copper kettle. Now, if I have a copper kettle and I see that I have another copper kettle that has been tarnished with copper oxide, I can say that copper can tarnish. That is a chemical property. If I look at the other kettle and say, this kettle, how do I want to word this? The kettle is tarnished. Has it already happened?
You said it is tarnished, right?
The kettle is tarnished. Has it already happened?
Yes.
That's changed. If something's already happened, it is changed. If I'm saying can be, or this copper, if I leave it out in the air, will be tarnished. If I make any sort of future statement like that, it's a property. If I make a statement such that it has already happened, that is a change. That is the totally, in a chemical change, the original substance has already been converted into something else. Now, let's think about this. I've converted it. Do I have a new substance? Cute dog, Samir.
Yes.
Samir, cute dog.
Thank you. I'm sorry. They heard you talking. They came to investigate.
Are they corgis?
They're poodles. I think they're toy poodles, or they're supposed to be.
Again, you want to distract me? Talk about dogs. Dogs, travel, or baseball. All right, my question is still out there. If I've changed it, do I have a new substance?
Yes, because you changed it.
I changed it, I've got a new substance, okay? What are the chances that my new substance is going to have different physical properties than my old one?
If it's a chemical change, it will have a higher chance.
If I have changed it into a new substance, that new substance probably has different physical properties than the old stuff. So guys, when we're doing experimentation, this is what we're using to determine if a chemical change has taken place. We're observing the chemicals before we mix them. We mix them, then we observe what happens afterwards. This is how we tell that there has been a chemical change. Does this make sense to you? Charlie,
Yes.
is it making sense?
Yes.
Yes, it is.
All right. Has anybody, this is the third time I've asked this question. I haven't gotten a positive response yet. Has anybody ever been to Florence?
I have.
Who was I?
Faye.
Faye, good for you. Absolutely. Have you ever been to Florence? You've been to Florence. Have you been to the Piazza where the Uffizi Museum is?
Yeah, I was in there. Mhm.
You were in the Uffizi? Wonderful. Absolutely perfect place to be. Guys, if you ever get to Florence, you got to go to that museum. In any case, Faye, the plaza. Did you know that in that plaza, that used to be filled with marble statues?
I did not know that.
If you go in the plaza today, there are all kinds of replicas. One of the most famous statues there is the rape of the Sabine women. That is in there, but it's kind of like a concrete replica. They cannot keep them out in the plaza anymore because of the fact that marble is a base. We have acid rain. The acid rain reacts with the marble, and some of the most famous statues we have are being destroyed by the acid rain. We are undergoing a chemical change. Okay? It doesn't look like it did before, does it? Let me see. I'm gonna bother somebody else I haven't bothered before. Javier, yeah, I haven't bothered you technically yet, Javier. Javier, are you there?
Yes.
Okay, Javier, what does steel look like?
It's gray, shiny, looks like metal.
Gray, shiny metal. Is it kind of dense?
Yeah.
All right, now describe rust.
Brown, it's rough, the texture, and it's flaky.
Okay, we got something that's really dense versus something that's flaky. Property of steel, dense. Property of rust, flaky. Property of steel, shiny metal colors, shiny silvery color. Rust, brown. Different property changes. So we've gotten a property change. We've observed property changes occurring. Let me redefine that. We have our properties of our chemical are different from what they were before. So we have a chemical change. Is that kind of making sense?
Yes.
Faye, you're out there, Faye.
Yes.
Okay, Faye, have you seen or bought a pair of acid wash jeans or bleached jeans?
Yes, I've seen them. I've never bought them.
Okay. What's the color of blue jeans before you add the bleach? Hint. They're blue jeans. What's the color?
Yeah, blue.
Thank you. Thank you so much. This is not the hardest question I'm going to ask this semester. All right, you have the blue jeans. You add bleach to it. Put it in the washer. What happens?
It turns it like a white or a lighter color, depending on how much of it.
In effect, what has happened is the bleach has changed something. It's changed the dye. So the property before was blue. The property now is kind of a whitish. I have changed the color.
Mhm.
Is this kind of making sense as to what the changes are, what properties are, what chemical versus physical are?
Yes.
Okay, now we're going to switch to your PowerPoint because it's not going to do me any good to talk about their experiments. Okay. Now, again, our whole hypothesis here is that if the properties of something change, then there's a good chance we have different substances. If we have different substances, it's undergone a chemical change. Okay? I've already given you the copper chloride answer. Basically, what I said there was I just took the copper chloride, dissolved it in water, changed the color of the water, but I'm not really changing anything because all I got to do is evaporate the water away and I get the blue crystals back. That is a physical change. On the other hand, if I take a clear solution of potassium thiocyanate and a clear solution of iron nitrate, and I mix them, and I get a blood red color, do I have a change in the property. I have two clear solutions. Now I've mixed them. I have a blood red solution. Have I changed the property?
Yes, you have.
Yes.
Do you think I've undergone a chemical change?
Yes.
I think so, yeah.
It looks like I've created a whole new substance that created the blood red color. Come on. Oh, I'm not in a slideshow. Why do computers do what you tell them to do rather than what you want them to do? If somebody can explain that, you get an A for the semester. All right, I'm telling you right now, if I have a cobalt-3 compound, they're red crystals. If they're dissolved in water, they have a red solution. Hypothetical situation. I take cobalt metal, which is a dull metal-like substance that's fairly dense. After 20 minutes, I put the cobalt metal into a clear colorless solution. After 20 minutes, I have a pink color. Did a reaction take place?
Yes.
Yes.
Because when I first put the metal in there, the solution is colorless. I have changed the solution such that I've now made it pink. Can anybody figure out what actually happened in this hypothetical?
Cobalt particles bonded with the water solution.
Nope, not quite, Charlie. Not quite. What's the cobalt turning into?
A liquid?
How's it getting into the liquid?
It's dissolving?
Okay, but it has to undergo something in order to dissolve. What is the charge on cobalt metal?
Is it that's one of the in-between, so is it a positive or neutral?
Copper metal or cobalt metal. If I just have cobalt metal there, what's the charge?
It's a transitional metal, so depending on what it's with, right? That's what the charge is?
If you pick up cobalt metal, are you going to get shocked?
No.
Because it's neutral, right? Whenever you see something described as a metal, it is neutral. All right. What about cobalt Roman numeral 3? What's the feature about that?
Oh, it's a +3.
It's ionic. It's a +3. So in effect, what we have done is we have taken our cobalt metal. It has lost 3 electrons. When it loses the 3 electrons, it becomes an ion. It dissolves in solution. Solution becomes red. Does that make sense to you about what's happening here?
Yes.
Let's see about it. James, you're out there, James. I haven't bothered you yet. James?
Yes.
Okay, good. Do you know what the Statue of Liberty is made of?
Copper,
What color is copper?
brown,
All right, what color is the Statue of Liberty?
green.
Now, wait a second. You just said the Statue of Liberty is made of copper and that the color copper is brown, yet you just admitted to me that the Statue of Liberty is blue. How can that happen?
The copper oxidized.
The copper underwent a chemical change. It oxidized to copper oxide. We have a chemical change. Arthur, you there, Arthur?
Yep.
Arthur, have you ever heated up? Do you remember the magnesium experiment? The video of the
Yes.
magnet. What happens when you put magnesium into Bunsen burner?
Isn't it like have like a flash of light as it's like heating
Right.
up?
This is a bright light. If you stare at it, you will go blind. As a matter of fact, it's so bad anymore that I can only look at it from my periphery. I've seen it too many times. So we have a bright light. But also, if you look at that magnesium, after you take it out of the flame and you look at the very edges of the magnesium, you're going to see that there is a fine white powder. What was magnesium before we started? Arthur, what does magnesium look like?
Isn't it more like a like actually at least some solid type of like metal?
What's a typical color for metal?
Like more like a silver, like shiny, like type of appearance.
Guys, if you're ever asked what the color of a metal is, choose either silvery or gold. 90% of the chance you'll get the answer right, or 50-50. You got a 50-50 shot at it. So magnesium is a bright silvery metal. That's the property of magnesium. After we put it in the flame, we have created a fine powder, fine white powder. Have we changed the property?
Yes.
Do we have a chemical reaction?
Yes.
Another key here. When you put that magnesium into the light, into the flame, you have a bright light. Light is energy. Anytime you have a release of energy, that means that something must have happened to release that energy. And if something must have happened, you have a chemical change. It works that way for light generally. You gotta be careful when you are looking at heat, because when you dissolve things, sometimes the solution will get hotter, sometimes the solution will get colder. It's not 100%, it's not 100% indication that a reaction has happened. All right, it's an indication that it may have. You just got to look what's happening. For example, if you put sodium chloride in water and you feel it, it feels like it got a little warmer. Was that a physical change or was that a chemical change?
Chemical.
What's happening? I'm putting sodium chloride in water. If I evaporate the water away, am I still going to get that sodium chloride back?
Yeah.
Yes.
So you got to understand, if we are dissolving something, that's always going to be a physical change. Now, if I add, let me see, if I add sodium hydroxide pellets into hydrochloric acid, I get extreme heat. Am I just dissolving it?
No.
I'm having
No.
the hydroxide react with the H of the hydrochloric acid, and I'm getting a chemical reaction. The chemical reaction is causing the heat. You got to be careful with heat. All right. How many of you have done the classic volcano experiment? You take baking soda, you add vinegar to it. Has anybody ever done that?
I've actually never done that.
Never?
I think
Samir?
I did it once.
Okay, good. Samir,
I've
you might.
seen it done. I've never done it myself.
Okay, either one of you. You put the vinegar into the baking soda. What do you observe?
I think it starts to bubble, right?
Bubbles. What are bubbles? How do you make bubbles?
Chemical reaction.
No. How are bubbles made? I can make bubbles without a chemical reaction. Just give me a straw and a bucket of soap water. How do you make bubbles?
It's usually usually it builds up to it, right? There's like usually pressure underneath. Like you can create bubbles by just breathing, like pushing a straw into like a soda or something.
Yeah, absolutely. But what are you doing? What's going into that soda, Samir? Thank you,
Gas?
Charlie. Thank you, Charlie. You're putting a gas in there. And generally speaking, what is happening is when you make a bubble, you put a gas in something that contains that bubble, that contains that gas, until the pressure inside gets too big and it bursts the bubble. Okay? Like right now, guys, I'm putting a lot of gas into you and I'm waiting to burst your bubbles. The jokes don't get better than that. Sorry. So now let's look at baking soda. Are there any bubbles in the baking soda? Are there any bubbles in the vinegar? We mix them together, we get bubbles. We create a gas. We have a property change. Okay? Now, we have an additional thing. A second part of the experiment. All right? You put a lit stick in, all right, you add the vinegar, it bubbles up, bubbles down. You then put a lit stick in the air above the reaction. It goes out. You put a lit stick above vinegar, no effect. Lit stick above the baking soda, no effect. Anybody have an idea what gas we're creating when we put that stick in there? What do you put fires out with, guys? What do extinguishers have in them?
Carbon.
Is it some form of sodium?
Nope. Somebody started it. Carbon
dioxide.
Carbon
CO2.
dioxide. So we're putting this stick in there and the stick is going out. What's actually happening is I'm creating a gas. I've now gotten an indication that that gas may be something like carbon dioxide, definitely is not oxygen. So I've got a change. I'm going over and over these things, guys, because this is what you need to be looking for when you have the experiments right before you. I have another experiment. If I put hydrogen peroxide, a clear liquid, no bubbles, and I add to that potassium iodide, a white solid, no bubbles, I put them together, I get bubbles forming. Did I have a chemical reaction? Do I have a chemical reaction?
Yes, it would want to be the form of gas that's escaping.
That's a form of gas. I didn't have gas before, I now have gas. Good indication. Now I light a stick, I put it out, it's still got an ember there. I put it in the air above the reaction. The flame relights. I do that over the hydrogen peroxide. I do it over the white powder. The flame doesn't reappear. What do you think I produced?
Really oxygen then?
Oxygen.
Yeah.
So I'm producing oxygen. I didn't have oxygen before. I now have enriched oxygen. I have a chemical change. All right. You have a clear yellow solution of lead nitrate, and to that you add a clear solution of sodium chloride. They're clear solutions, no solid in them. I put them together, I create a solid. Did I have a chemical reaction? Say, did I have a chemical reaction?
Yes, because a precipitate was created.
I've got the new property that this new substance doesn't dissolve in water, whereas before everything dissolved in water. That's an observation I'm making. already talked about this. All right. Now, I don't agree with giving you this right now because you haven't had the chem reactions. You're going to have to pull back, guys. You're going to have to grab information you had last semester. Okay? Now, you put magnesium with HCl. Can anybody look at this and tell me what kind of reaction? Oh, Mr.
A
Popovich.
chemical reaction?
Yeah, chemical reaction, but what type of chemical reaction?
Isn't it like bubble and flake?
No, no, no. I'm not looking for observations right now.
Are you
I'm
actually
looking
assuming, are you actually assuming like a single or double replacement or?
Okay, you got a choice. 50-50 here. What's it going to be? Single or double?
Single.
Single.
Single. All right. What happens in a single displacement? Anybody know the Flintstones?
Yeah.
Who are the Flintstones?
Oh,
They're
it was
cavemen.
it was a cartoon where the characters were like kind of like cavemen living
Who
like
are they? What are their names? Give me their names. I need
Uh,
names.
was it Wilma?
How about
Dino
Wilma?
the dinosaur.
Dino doesn't count. I want the four main characters. And I don't want to hear Pebbles or Bam Bam. I want the four main characters for the Flintstones.
But you got Fred.
Fred.
Wilma.
Hey, Fred. Hey,
Wilma.
Wilma.
Barney.
Barney and this is the hard one.
I forgot Barney's wife.
Eddie.
Betty, yeah.
Okay. Well, Wilma's back at home. Fred goes out to a bar. He's in the bar and he happens to look over and he sees Barney and Betty. That brunette looks hot to me. So he goes over, shoves Barney out of the way, and hooks up with Betty. Charlie, have you ever dumped a guy? Never? I don't believe that. You have never dumped a guy. Probably you left him for roadkill. I know. He's on the side of the road crying today. This is what happened. This is what
I
Betty
realized.
did. Betty.
I didn't realize I was
dumped
on
Barney.
mute.
Betty dumped Barney and grabbed onto Fred. So we have a new compound. We have the Fred-Betty compound. Poor Barney is left on the side of the road crying his eyes out. So what we have, if we have chemicals, same thing. They have attractions too. The magnesium has an attraction for the Cl. So when we put these two things together, the magnesium, it hooks up with the chlorine. Then we have the poor little old hydrogen off by itself. That's what happens in a single replacement reaction. But it's not quite that simple. For one thing, hydrogen is a diatomic molecule. It only exists as H2. Again, a lot of this stuff, I'm hoping I'm pulling back information from last semester. If you have hydrogen by itself, it only exists as H2. There are 7 of these kinds of compounds. I want you to write this down. Have no fear of ice cold beer. Have no fear of ice cold beer. Have hydrogen.
Hydrogen, oxygen.
No, nitrogen. Let me do this. Have hydrogen and nitrogen. Fear, fluorine. Of oxygen, ice, iodine, cold, chlorine, beer, bromine. These are the 7 elements which cannot exist alone. They have to have a partner. They're afraid. It's an awfully cold world out there. Hydrogen needs another hydrogen to feel comfortable. So it exists as a molecule, H2. So when you're balancing this equation, you have this going to MgCl plus H2. Then you have to balance the Mg and the Cl. Mg is a +2, Cl is a -1. You need 2 chlorines. Again, I'm sorry to give this to you this soon, but this is not what I had intended on doing. You recognize a single displacement if you have a neutral metal and an ionic compound. Anytime you have a neutral metal and an ionic compound, you have a single replacement reaction. Now, yeah. So we predicted one of the products is H2. So riddle me this. If this reaction, if I mix these two things and I produce hydrogen, what are you expecting to see in the chemical reaction? At room
Bubbles.
temperature, at room
bubbles?
temperature, what is the state of hydrogen?
Gas.
So does magnesium metal have gas? HCl is a gas, but when it's dissolved in water, if you have hydrochloric acid, does that have a gas that's evolving on it? So what are you looking for in this reaction? What was the last time we had a gas form? What did we see?
Bubbles.
Bubbles! Bubbles are so nice. Bubbles are great because they immediately tell you you have a chemical reaction. Quickly, what type of reaction is this?
Single displacement.
Single displacement. By the way, single displacement, single replacement. I don't care. Just use whatever you want. All right. They both are the same to me. So if it's a single displacement, what are my two substances?
That are replacing each other, the zinc and the copper.
What compound do I end up with?
Zinc sulfate.
Zinc sulfate.
And?
Plus copper by itself.
Okay, plus copper. All right. Now, does anybody out there know what zinc looks like?
Shiny metal.
Okay. Remember, I gave you two choices, silvery or gold.
Silvery.
Silvery. It has a dull steel-like appearance. All right. What's the color of copper?
An orangish metal.
Like bronze, like color.
Okay. So if this reaction goes, what are we making? What's the metal we're making?
Zinc sulfate.
No, the metal. What's
Copper.
the copper? What color is copper?
Brown.
So did I have brown before? Do I have
No.
brown now? Do I have brown? If brown appears, did the reaction go?
Yes.
Yes.
If the reaction goes, then I had a chemical reaction. All right, same difference. Only, I got something different here. What kind of reaction is this one?
Double.
Double replacement. I got a great analogy for you guys. You guys weren't around for the 70s. I was. Has anybody heard what a key party is?
Key party?
Key, K-E-Y, key party.
Is that where everybody trades each other's keys and they, I think, go home with somebody's house?
I'm sorry, who are you?
Samir?
Samir, I have new respect for you. You are a man of the world, Samir. He's absolutely right. What happens is couples go to a house, and when they go into the house, the guys all drop their keys into a big bowl. They blindfold the women, and the women reach in and grab a set of keys. Whoever's keys those are, the woman goes with that guy. This is the same thing. We have Fred and Wilma and Barney and Betty. Well, they get together and Fred says, I'd rather be with Betty. So we get the hydrogen linking with the sulfate. And Barney says, if you're going to take Betty, I'm grabbing Wilma. So the copper grabs the chlorine. We get a replacement of the cations and the anions. You identify a double replacement reaction by looking at the reactants, and you have two ionic, give me my arrow. You have two ionic compounds. Hydrochloric acid is ionic, copper sulfate is ionic. Two ionic compounds identify double replacement reaction. Okay. What type of reaction is this? Faye? Any idea, Faye? Go ahead.
Double displaced. Oh, wait. Ooh, I want to say double displacement.
You're right. But there's a little addition. So, Faye.
With an acid?
Okay. Faye, I'm sorry. My bad. Hold on a second, Faye. I got ahead of myself. You're absolutely right. This is going to be a double displacement. And what's going to happen is the copper is going to link with the bicarbonate and make a solid solution. The sodium is going to link with the sulfate and it will still remain in solution. So by the fact that I have now created a substance that doesn't dissolve in water anymore, I've created a new property. Chemical reaction has occurred. Now I'm going to have a similar reaction happening. Maybe a little later. Again from this, what kind of reaction is this?
Double.
Okay, Faye, you have reached your quota of correct answers. I now know who I can depend upon to give me a good answer. You're smiling still, Faye. Double displacement. I have two ionic compounds. Double displacement. What happens here is the copper links with the OH and it makes a precipitate. I get a precipitate out, something occurred, new properties, chemical reaction. Tin, what kind of reaction is this?
Single displacement.
Single displacement. So what are my products going to be?
It will be MgSO4 and copper.
Okay. Mg, what's Mg look like? Do you remember?
Silvery.
Silvery. What's copper look like?
Brown.
Yeah, okay. Now, Tin, if this reaction goes, what do you anticipate seeing happen?
The magnesium grab the SO4, then leaving the copper.
Okay, so
on the side.
Remember what you said. Magnesium is silver, copper is brown. What are you going to note the appearance of?
The copper.
You're going to note the brown color. Okay? Does that make sense, Tim?
Yes.
Now, this is the one I wanted to get to. Who's got a challenge out there? Who wants a challenge?
Well, I'll go ahead.
Max? So who was that?
It wasn't
That was
me,
Art.
but I'll do it.
No, who said, who volunteered first?
I did, Art.
Okay. Please, guys, don't answer I did. Right now I have 13 I dids out there. Okay, Art. And I will now change your name to Art. Art, what kind of reaction is this?
It'd be a double replacement.
All right, what are my products going to be?
So I know the sodium's gonna combine with the chloride, and one portion of the probably would be, is it carbon dioxide or water should be one portion of the products?
Actually,
Since you
you're
have-
right. You're right, but I wanted you to do it step by step.
Okay.
You said it double displacement. Yes, you're right. The sodium reacts with the chlorine. Absolutely correct. What's left, Art?
We still have carbon, carbon with oxygen and hydrogen. So
this hydrogen, let me see. First, the hydrogen on the HCl links up with the HCO3 to make H2CO3, right?
Yeah.
All right, now I have H2CO3. Do I have a stable compound that I can pull out of H2CO3?
would be an H2O since
H2O, is H2O a fairly stable compound?
Yeah.
So I have H2O. What does that leave me in H2CO3 if I take H2O away? What does that leave me?
Then you have one carbon and then two things of oxygen.
Which is
CO2. Yeah,
CO2.
CO2 then.
So I have a compound, H2CO3. From that, I can make two very, very, very stable compounds, water and carbon dioxide. And that is what happens when you have either a carbonate or a bicarbonate and you mix it with acid, you make the salt, you make carbon dioxide and water. Carbon dioxide, what state of matter is it, Art?
As a gas.
So, do I have gases before?
No.
So, what do you expect if the reaction goes? What are you expecting to see?
You see some form of bubbling.
Bubbles! Bubbles, more bubbles. Who wants a lob? Sake, do you want a lob?
Maybe.
Okay, Saki. I'm mixing ammonium chloride, NH4Cl, and water. Does anything really happen?
No.
No. All I'm doing is taking the ammonium chloride and dissolving it in water. That's all this chemical reaction is saying. So if that's all I'm doing, do I have a chemical reaction or chemical change, or do I have a physical change?
Physical change.
Physical. All I'm doing is dissolving it. Okay, guys, I believe what I just did was take you through each of the experiments. Now, quickly, and I realize I've been here an hour so far, but quickly, I'm going to try and show you what's happening. Can you all see the screen that's on there now?
Yeah.
Yes.
All right, so we're going to go to course content. And luckily enough from last night, it's going to pull up the right chapter. Now, you have to look at the video because the video is going to give you the before observations and the after observations. So you're going to need to have that. I am going to pull back a second and go to the lab manual. I'm sorry, I just had something I have to show you before we start this. And it'll take a few seconds to pop up. Good. All right. And now I got to get rid of you guys over here. There we go. You are seeing the manual, correct?
Yes.
All right.
Yes.
Now, remember, you owe me a notebook on this, okay? Ultimately, the assignments that you have due next Wednesday night at midnight. You have the results section from this. You have the post lab from this. And believe me, I looked at the post lab last night. Guys, there's nothing to the post lab. So you have those two things due midnight next Wednesday night. You also have the pre-lab for, I believe, the measurement. I think measurement is our next lab. In any case, it's going to be the pre-lab for the next one. So you have those 3 assignments, and you have to do the lab notebook. Guys, do it right first. If you do it right first, then I'm going to be able to give you the whole points the entire semester. If you don't do it right from the very start, I'm going to keep badgering you. I will keep badgering you until the very end. All you got to do is prove that you can do a notebook right once. Then you have to continue doing the notebook, but I'm not going to scrutinize it as much. Part of the notebook is a data table. I don't like this one. I don't like this one for one specific reason. Do you see the space they give you for appearance of reactants and the space they give you for observations? Those should be more or less equal, but you can kind of squeeze it in there if you want. All right. What you're going to do for all the experiments, you're going to look at what the reactants looked like before mixing, then after. Before mixing, it's going to be the appearance of the reactants. After mixing, it's going to be the observations. Then you are going to have to make a conclusion. Understand this. Observations are what you sense, what you can see, hear, feel, touch, or smell. Those are what observations are. Conclusions are the logical deductions from those observations. In this case, our observations are the appearance of the chemicals after mixing. Our deduction is going to be whether it's a chemical or physical change. Any questions on this, guys?
Do we have to use this sheet in the
No,
lab manual?
no. You don't have to use it. You can handwrite it in if you want. If you do use it, it has to be put into the notebook. It has to be taped there, stapled, glued, concreted. I don't care. It's got to be in the notebook. If it's not in the notebook, it doesn't count. Any other questions?
So for the results section, we're just saying if it was a chemical or physical change for each
for the type of change column. I mean, I don't even care if you put a P or C there. That's enough for me. Okay.
And that will be in a results section, but just in a sentence?
No, that is going to be your conclusion in your data table. You still have to write the results section.
Okay.
Which means you're going to do all this. You're going to say all this over again. It's the nature it's the nature of this particular lab. Any other questions about the notebook or what I'm expecting thereof? I've given you the PowerPoint. It's under instructor notes at the very bottom of the modules. I've given you a PowerPoint on what I expect, and I've given you a decent exemplar of a notebook. Same place, instructor notes.
Are we going to move the post-lab questions into our notebook, or is that just going to be?
No. If there are post-lab questions, you are not required. If there are, right, let me back off because I have to explain things in detail. If there are post-lab questions in the printed lab manual, If there are post-lab questions there, you do not have to answer them. They may help you answer the post-lab questions online. You have to answer the post-lab questions online. You don't necessarily have to answer them in the lab manual. Is that clear, ladies and gentlemen?
Yes.
Yeah.
All right, so I'm going to go back to the results. Why do computers do what you tell them to do rather than what you want them to do? If somebody can explain that to me, you got an A in the course for the semester. Okay, now I got to get back down to your class. Course content, and hopefully that'll pop up again. Yay, nope. I gotta go find it. Chemical and physical changes. All right, what he does give you, he gives you a link to a video in which it discusses double displacement reactions. I don't know why he only gave you this one, but if you're interested in single replacement reactions or single displacement reactions, all you got to do is type organic tutor, comma, single displacement reactions. A video will pop up. Either you, I like organic tutor better. The guy has a very monotonous voice, but he goes through things in minute detail. Organic tutor, Khan Academy. Two choices for you for videos. Okay, now we're going to get into the results section. And we're going to do preview because that's the way I get in here. And start quiz. We're all seeing this, right, guys? We're all seeing this? All right, these are gonna be all matching or multiple choice questions. Your first reaction is mixing magnesium with HCl. These are your choices for observations of what happens after the mixing. You get a solid change in color, formation of a precipitate, solid solution changes color. These are various choices. Choose everything that is applicable. There can be one answer, there can be more than one answer. And you get graded on this on a yes/no situation. For example, if you click solution gets colder and it didn't, you get that portion wrong. If you click formation of gas and it does, you get credit for that. So basically your 10 points gets divided into 6 portions and each one of the sections is worth 1/6 of 10. Then you have another conclusion right below. Was it physical or chemical? Next reaction goes to the second experiment, zinc and copper sulfate. Same thing, gives you a choice of, this one is only 3 or 4, gives you 4. Each one of these answers is worth 2.5 points. You do this for each experiment that is encountered in the experiment. Questions? At the very end, yes, you're going to have to go through predict products and balance the reaction. Oh, I'm sorry, excuse me. What you're going to do, you're given this. He wants you to predict coefficients and compounds, balanced compounds as the products. Are there any questions? Questions? Okay, exiting, getting exit out of here. And you're gonna really love the post lab for this. This is like a gimme 30 points, guys. Post lab is gonna be multiple choice. Preview. Start quiz. Mothballs gradually vaporizing in its closet. Is it a chemical or physical process? You have 5 questions like that. And that's your whole post lab. Okay, having said that, generally speaking, this is generally one of the poorer labs I get back. That's one point I want to make. So you got to be very careful looking at the videos and making your observations. Listen to what Dr. Musgrave says. In certain circumstances, he'll feel a test tube and say, oh, this is getting hot. So as you're going through the video, take notes of them. That's the one point that I have for this. And, oh God, I've just lost my mind. There was a second point. And, sorry, it's just completely flashed out of my head. Questions, guys? Oh, that was the point. Yeah, thank you. All right, do you remember there was a list? There was a list of things that, observations after mixing of the chemicals, right? Do you remember that in the results section? If you firmly believe, and believe me, the quiz is not 100%. If you firmly believe that you got an answer right, bring it to my attention. This is the one time I'm going to encourage this entire semester. If you believe you got an answer right, that you heard Dr. Musgrave say something, bring it to my attention and I will correct it. But you have to have reason for saying that this answer was wrong. In other words, if you got the answer wrong, it was marked wrong, and you believe you heard something, go back to the video, verify it. And if necessary, give me a time in the video that it happened. That will give credence to your getting the answer correct. Other than that, ladies and gentlemen, other than that, Mrs. Lincoln, how did you like to play? That's the best one-line joke of all time. I got nothing for you. Generally speaking, yes, I've been an hour and 15 minutes. This has been a little longer than I normally like to take, but unfortunately, there's a lot of material here. Did I explain things well enough to you? If you didn't understand, if I didn't explain it well enough to you, please stay afterwards. I'll be happy to go through it again. Other than that, I got nothing more to say, guys. Unless you want to stare at this hat for the next hour and a half. Bye-bye.
Thank you.
Have a good day.
And guys,
Have a good day.
Another thing, when you're leaving class, do it quickly because sometimes people want to hang around afterwards to talk to me in private. Okay? Good enough. Happy to see you. I will see you again. Looking forward to seeing you again next Thursday, guys.
See you next Thursday.
Thank you.
Bye.
Have a good weekend.
Okay, thank you.
Good weekend.
I've got a question about the video.
Yeah, Faye.
For I think it's the copper sulfate and HCl, hydrochloric acid.
Okay.
I think in the video he said they didn't see really anything change, but when you look at the chemical reaction, it does change, correct? Since it's a,
No. All right.
oh, it doesn't?
All
Okay,
right.
thank you.
Faye,
Yes.
if you want to go back, remember single replacements? You looked at the activity series. Do you remember
Yes,
that?
that's what I,
If you look at, I want you to look at the activity series and look at hydrogen versus copper.
oh,
And then-
hydrogen is more active than copper.
So
Okay,
is it going to react?
no.
There we go.
I was looking, I thought it was a double displacement.
Oh,
That's why I got,
I'm sorry. You're absolutely right.
but hydrogen isn't on the solubility chart that my chem intro teacher gave us.
Okay, well, think to yourself. It's copper sulfate, Faye? All right. If you double displace it, then you put hydrogen with sulfate, right? What is H2SO4?
Hydrogen sulfate?
No.
H2. Oh, H2 is a gas?
Nope. H2SO4. Put that together. It's sulfuric acid, Faye.
Oh.
Is sulfuric acid water soluble?
No. Yes.
It's an acid. It's sulfuric acid. It is soluble in all degrees.
Okay.
All right.
Acids. Yep.
Not all acids. Sulfuric acid is very, very soluble in water, though.
Okie dokie.
So there's your answer.
Okay. Thank you, Professor.
No problem. Have a good day.
You too.